Can you hear me?
Okay. We're very happy to have Nathan tell us about Ramification in geometric Langlands.
Okay, thank you for the invitation. It's a pleasure to be back. If you have any question, let me know. If you want some physics statements or more math statements, I'll do my best to please. So yeah, so time permitting, we'll discuss applications in gauge theory of a construction in conformal field theory. So what is the construction? Well, the original program is the one of Beilinson and Drinfeld, who in '91 published a paper where they defined the geometric Langlands program. And so this program originally is a statement about equivalence of categories, and mostly due to a program of Frenkel has been recast now into equivalence of, well, certain spaces of conformal blocks in conformal field theories. So that's the part that I'll be mostly interested in. If you want, in its earliest version, I'll start at the bottom, you have something called the classical W-algebra, which is labeled by a simple Lie algebra, G. So let G be simple. Later, I'll take G to be simply laced, just so that the formulas are easier. But you can take any simple Lie algebra. And in this talk, I'll have parameters Q, T, H bar, which we'll take to be transcendental. It will not be equal to roots of unity, very far from it. So there's that, transcendental. W algebras are also labeled by something called the nilpotent orbit of G. In this talk, it will always be the maximal nilpotent orbit, so I will not write it down. Sometimes I'll use the letter R, which means the rank of the Lie algebra G. And the Lie group associated to G will be simply connected. Simply connected. Lie group with Lie algebra small g. Okay, so in its earliest version, this algebra, what is the W infinity algebra? It's the algebra of functions on the space of connections on the circle. Well, actually of gauge equivalence classes of connections on the circle. So where is the circle coming from? Well, we're studying a Riemann surface C, which in this talk will be a cylinder. And you put punctures on your Riemann surface. So when I say the space of functions on the algebra of functions on the space of connections on the circle, imagine excising the punctures. So you have like little holes everywhere. This is where this circle comes in. So when we say connections on the circle, we mean circles around each puncture. So this is the meaning of circle here and why it's related to a construction on a Riemann surface. And so the Feigen-Frenkel isomorphism was a very important result, which shows that this thing was isomorphic. So maybe I'll write isomorphic to the center of the universal enveloping algebra of G. Well, maybe I'll write it slightly differently, but at critical level, at level K equals minus the dual Coxeter number. So you could, what is this? This is a commutative associative algebra, which has actually a Poisson structure. And so in terms of, it has a Poisson bracket, you could describe the center of this, and so what is G, Langlands dual hat? Well, Langlands dual equals G if G is AR, DR, or E 6, 7, 8, and Langlands dual of BR is defined as CR, and Langlands dual of CR equals BR. I'm using Dynkin notation. AR means SL and SLR plus 1. This is SO2R. E6, 7, 8 are exceptional. I should also write G2 and F4. they're mapped non-trivially to themselves under Langlands duality. Okay, so Langlands duality will exchange short and long roots in your algebra. So in these guys, the roots all have the same length, so they're invariant. But for G2 and F4, you have long roots and short roots. They get mapped into each other, but the relabeling leaves you in the algebra. It's non-trivial, this duality, for SP to R and SO to R plus 1. It sends you from one algebra to a totally different algebra. So that's the only place where Langlands duality for Lie algebras is non-trivial. So at the level of what I'm going to talk about, I want to talk about conformal blocks on this Riemann surface. And so the blocks have as arguments a certain number of parameters, which will be labeled by data at these punctures and at the two ends of the cylinder. And roughly speaking, it's a map which takes you from a tensor product of various modules that label the data on this Riemann surface to the trivial module. Very roughly speaking, that's what we mean by conformal block. And so here, G, we see that the dual algebra appears, and it's an affine, untwisted affine Kac-Moody Lie algebra associated to G Langlands dual, and it's labeled by a level, which here is fixed to be a negative integer, which is just fixed by representation theory called the critical level. Okay, so at the level of blocks of this thing, conformal blocks here, can be shown to be isomorphic, in fact, to certain conformal blocks at this algebra, but this is a very degenerate case. From the point of view of CFT, especially if you're a physicist, this algebra is very unnatural to consider. So in fact, instead of talking about blocks of there and blocks of this, as a physicist, the natural thing you want to do is consider an algebra that shows up everywhere in physics, which is a W algebra with a parameter deformation, and consider the isomorphism to here, G, very naturally away from critical level. So K, Langlands dual. And so what is this algebra? Well, you can think of it, if you start from this algebra, as, well, this I told you is a commutative Poisson algebra. So Poisson brackets, physics quantization of the Poisson bracket gives a Lie bracket with some kind of quantum parameter, which actually here shows up as this beta. Physically, you want to think of beta as labeling the central charge. If G is A1, so the SL2 case, this algebra is called Virasoro algebra. So really now we're talking about diffeomorphism on the circle with central extension, right? So you have no central extension here when the centrally extended algebra brings you here. So that's like the Virasoro algebra is the central extension of the DeWitt algebra. So that this kind of statement, and so Virasoro is the case G equals A1, but for any simple Lie algebra G, there's such an algebra that exists. And the statement now is that blocks of this algebra would be isomorphic to blocks of a Kac-Moody algebra, which is this one, so at generic level. So this is very familiar to physicists as well, because these are WZW models. Okay? So in practice, if you don't want to start here, you can start from an algebra here, which is G at level K, G hat, and there's a procedure to go to this algebra called the Drinfeld-Sokolov reduction, which in fact was first used here for the classical W algebras. These are called classical because they have no quantization parameter, and these are called quantum, sometimes W algebra. So this procedure to go from an algebra untwisted affine Kac-Moody to a W algebra is well known. It's called the Drinfeld-Sokolov reduction. And so what is the full general statement here? This is still kind of unknown. I mean, we want to think of the blocks, the conformal blocks, as certain objects in a category. So really, the statement here, this is called quantum geometric Langlands. And again, the quantum here refers to the parameter beta encoding the central charge, and here the level of the algebra. So this would just be geometric Langlands or classical geometric Langlands. And you get from here to here by just taking beta goes to infinity. And here the classical. But really, this is an equivalence of categories. The objects of this category are certain representations of the algebras. And exactly which representation, I think to this day, is still an open problem. It's known for certain simple representations, while modules on this side, for instance, that there is such a statement that holds, but the full extent of this equivalence of categories is still, I think, not fully established. So how general is the statement? We don't know, but we have like a lot of specific representations of these algebras for which we can establish a correspondence or equivalence of conformal blocks. And so, yes, but at the full statement of categories, it's not clear yet what is the full generic statement. So in 2017, it was realized that these two algebras are further limits of something that's very natural. And so this is due to Aganagic-Frenkel-Okounkov, AFO, I'll say for short. And they call it the quantum Q-Langlands correspondence, for lack of a better name. It's a bit unfortunate, there's lots of Q's now. The quantum here was the quantum there. And in the quantum group literature, people often talk about Q deformations. And so this is the Q of quantum groups from the 90s, from Drinfeld in the late 80s, and Drinfeld also later. So this is this Q, and this quantum is the quantum from before. And now I have an algebra WQT, depending on two parameters, also labeled by G, and you can show, or at least conjecture, that in some sense conformal blocks for this algebra, which we'll define in review, should be related to conformal blocks for, well, the natural thing to do in this Q quantum world. This is on the nose, what Drinfeld would say is the quantization, in the sense of Drinfeld, of this algebra. Not exactly this algebra, this is not a nice algebra to quantum deform, but its universal enveloping algebra is a Hopf algebra, and that can be quantum deformed. So you really consider the quantization, by definition, the textbook example of Drinfeld of the universal enveloping algebra of this guy at an arbitrary level. Here I have the level, I have h bar, and here I have q and t, so two arbitrary parameters on both sides. And Aganagic-Frenkel-Okounkov give and provide evidence for a dictionary which relates the parameters on both sides and from which you can derive kind of how they should be related. It's also interesting because before this paper in 2017, there were many attempts to also establish a dictionary for this correspondence, which does not look in earlier work like the dictionary you would get here. So, but nonetheless, both dictionaries are true. They're related by some dualities. But anyway, so here what do we have? H bar is Q over T. When I'm going to put Q to the lacing number, and I'll drop it a bit later. Lacing number is the maximal number of arrows you can have between two nodes in the Dynkin diagram of G. So if your algebra is non-simply laced, for B and C, NG is 2. For simply laced, NG is 1. For F4, NG is 2. And for G2, NG can be 3, is 3. Okay? So this is just 1, 2, or 3. And it will be 1 in most of the talk. I'll get there. Right. So this is, if you want, like a much more general statement. And very little has been studied about this algebra. It was defined in '98 by Edward Frenkel and Reshetikhin. So Edward has been the Frenkel I'm talking about this entire time. But I say that because on this side, the conformal blocks of this algebra were constructed as solutions of quantum Aganagic-Frenkel-Okounkov equations, and this was built by Igor Frenkel and Reshetikhin. I want to say 91, but so this is Igor Frenkel. Okay. Kind of a funny coincidence.
No, it's not a coincidence.
Yeah, well, I mean, what I meant is that, yeah, Reshetikhin's invariant under Langlands duality, and Langlands dual of Igor is Edward. So that's the, anyway, so, okay, and so if there is such a dictionary here, there's also the fact that, well, Q is h bar to minus the level shifted of the Langlands algebra. So with these two relations, you have a full dictionary relating the parameters on both sides. You can express Q and T in terms of h bar and the level of the Langlands dual algebra, and vice versa. Okay, so I won't have time to talk about it, but this dictionary implies also a relation to S and T duality in gauge theory in four-dimensional Yang-Mills. Maybe we'll talk a little bit at the end about it. Okay. Okay, so maybe I have to talk more about this algebra. This one is very standard and well known, but this one is not. There's many surprising things about this algebra. It is not isomorphic to WTQ of G Langlands dual if G non-simply laced. So if G is of type G2, F4, BR, or CR, then this algebra is not isomorphic to this. So this would have been nice, especially in the context of, but it's not the case. And there's various things you can do. So to recover the algebra that physicists like, again, this is the algebra that physicists like because it's the extension of Virasoro, which just has higher spin currents. It's the symmetry algebra of Toda conformal field theory, the chiral algebra of conformal field theory of Toda conformal field theory on a Riemann surface. So that's how physicists are familiar with it. So they're most interested in this limit, which is T equal Q to the beta, Q goes to 1, beta fixed. Okay?
Sorry.
Yes?
So you mentioned when G is not simply laced, it's not equal.
For G simply laced, it's true. Yes. Or if. A lot of technicalities appear when G is non-simply laced, which can be remedied in some form, but at this level, it is not the case. Now, this guy has other interesting limits. Like the most trivial limit was clearly not to take this weird scaling and scale like this. You could have done this, the simplest thing, which is to just set T goes to 1. And so if T is 1, you get W1Q of G. And so this is isomorphic to the center. Oh, I should be careful. I should write Q1. And this is isomorphic to the center of the quantum affine algebra. G, not Langlands dual, at critical level. So that's one such statement. That's that's one of the key results. In fact, the way Frenkel and Reshetikhin first thought about these algebras, as they were thinking about them as interpolating algebras between different algebras that we know better. In this case, were the quantum affine algebras. They knew the connection to integrability and so on. And so these guys kind of interpolated between this at the critical level, and ideally they would have wanted also another limit. If I have enough room, maybe I'll write it over there. Here, where you get Q goes to 1, that would have been nice, W1T of G. Unfortunately, again, in the non-simply laced case, this limit does not quite make sense in terms of representation theory of a quantum affine algebra. It is completely an open problem what this algebra is. So I should say that this algebra is also commutative and Poisson, so it's very nice. This one isn't. This one was commutative and Poisson. And so here I get another algebra which is not Poisson commutative if G is non-simply laced. Nevertheless, it has a subalgebra which is commutative Poisson. And this subalgebra, I will write an epsilon here and write Q equals e to the I pi over the lacing number of G, if G is non-simply laced. And so this weird limit had was a limit to an algebra which had a subalgebra, and this guy has a nice relation to the center UT Langlands dual G at critical level. So there was a connection to quantum affine algebras, but they weren't satisfied because they didn't know what to do with this epsilon. They had to, sorry? It gives a, yeah, so it's e to the I pi over ng, where ng is 2 or 3. If G is simply laced, the limit is just Q equal 1, and you have a nice story. In fact, yes. If Q, yeah, so in this case, Q would go to, you're not allowing ng equals 1. This is a limit for if G non-simply laced, and if G simply laced, the limit is this. So it's a very strange limit to consider, and they understood algebraically that if you take epsilon to 0 in some control way at the level of the algebra, you make connection with this algebra, but they did not understand the meaning of the limit of taking epsilon to 0 or this algebra in terms of the representation theory. It's I pi over ng in the. Yes, yeah. So you're right. So yes, yeah, that's why I would have said it's probably yeah, good. In which case, now I can get rid of this. So this is in '98. All of this is like old, and there was no progress on what the hell this limit means or what to do here. It's a subalgebra of W epsilon t, which I won't describe, but this one is commutative Poisson and this one isn't. So you have to do more work to identify an algebra which nicely maps to the center of like a quantum affine algebra. And so that's where this story about interpolating algebras come from. You see, in some sense, they interpolate between the center of a quantum affine algebra G and its Langlands dual with the different quantization parameter. And this looks very different from what Mina, Edward, and Andre found, which was that the WQT algebra itself admits a duality, not to a center, but to the quantum affine algebra with a very different parameter, Q over T, or Q to some number over T, for this algebra at an arbitrary level. So if you want, this is kind of a third updated new duality at this level. And I should mention that in 2022, very recently, Hernandez, Frenkel, and Reshetikhin understood a limit Q goes to 1, so none of this business, directly as an operation, formal operation they call folding on a simply laced Lie algebra. So they say that W1T of G is isomorphic to something called folding on UT G simply laced. So this is restricting to only representations that are invariant under the auto-automorphism group of a simply laced Lie algebra, simply laced, and yes, folding on this. H. Yeah. So, and this is closer to what we like in physics too. We have constructions coming from gauge theory and string theory, which suggest that you should want to think sometimes of these non-simply laced Lie algebras as originating from some geometrical construction via folding, very standard in physics. And so here they found that actually this limit is unambiguous and really produces this, but now what the interpretation is of folding at the level of the QKZ equations and so on, open problem. So the integrable system part of this folding on an algebra is an open problem for integrability. It's not understood what this means. Anyway, so that's, and then, you know, you take Q goes to 1, sorry, T goes to 1, and you recover this algebra, and here you take Q goes to 1, and you recover this algebra. In fact, here you recover an algebra which is W0 of G, like this, which is related by beta goes to 1 over beta. So this algebra here has a very nice isomorphism too, which is WNG over beta of G Langlands dual. So it turns out that on top of having some connection to quantum affine algebras or affine algebras, there's also isomorphisms of W algebras themselves that exchange beta with 1 over beta for the Langlands dual algebra. Right. So that's the story as it was understood, and it hasn't really been pushed further since '98. Yeah. This is W0 of G, not Langlands dual. And if G is simply laced, then it won't matter. But yeah, so this is isomorphic to W infinity of Langlands dual G. Yeah, right. So, yeah, exactly. So the limit here at this level of this algebra in the Q goes to 1 limit, I'm not sure is understood as now if I take T goes to 1, it's not known what the algebra is. But if G is simply laced, then the two limits are understood. If G is simply laced, you start by taking Q goes to 1, and then you take T goes to 1, and you end up with this, which naturally, because G is simply laced, is the same as this one. If G is non-simply laced, it makes sense that you should land back on this, but I don't think the limit has been studied carefully. So yeah. This folding operation is tricky to understand in terms of limits. So, but yes, I mean, the expectation would be that if I take T goes to 1 here, I should land back on this for G non-simply laced. And so but the point is that there should be a non-trivial statement. There should be some non-trivial new thing about folding at the level of classical algebras. Okay, so let me tell you about, in 3 lines, how to define these algebras so that you know what I'm talking about. And the main part of the talk will be to just tell you about the operators of these algebras. Or maybe I'll just take the other board. So, notation. I'll write this very often. A number in brackets Q means Q to the K over 2 minus Q to the minus K over 2. Okay, so the WQT definition, you start with a deformed W-algebra, a deformed Heisenberg algebra, sometimes called a Q-Heisenberg algebra. And again, I should write, technically QT deformed because Q and T both appear, but in quantum groups, people write Q for everything. So you have generators, alpha K, alpha B, M, whatever, which are based on commutator relations, which are Heisenberg relations, but kind of the Q analog. So Q, 1 over K, K, Q, K, T, delta AB, delta K minus M, A, B, they go from 1 to the rank of G. And these K and M, they're integers. In this case, maybe I'll exclude the zero mode. And so that's the defining relation of the deformed Heisenberg operator.
So
yes?
this is like,
oh, I made.
remember this.
I should be careful.
Yeah.
Yeah.
Like divided by q minus q inverse?
Yeah, so some people normalize by q minus q inverse. Not needed here, but there are, you can write a definition that does just that. Yes, so the limit produces something that slightly scales differently.
Okay.
So in particular, if you want to make sense of the undeformed Heisenberg algebra by taking the limit, now I have to redefine the generators by some power of, well, some factor that's q minus q inverse, precisely.
This one is alpha a bracket k. Bracket k is the
They're modes, they're integers. So that's literally just yes.
and they're not allowed to be zero?
You can, yeah, there's also the zero modes, but they commute with everything here. And the zero mode will enter the story in an important way, but let me just write it like this. This is some modification of the Cartan matrix. So Q analog of the Cartan matrix of G. Unimportant what it is, but just know that this is what this factor is. It depends on Q and T. Okay? So, definition of the W-algebra, I've given you this. They were first defined in free-field formalism, and by this I mean that you define an operator, SA of Y, some normal ordered exponent. Yes?
Q and T under symmetric
Q and T, yes, they do. So, for non-simply laced, they don't, and you consider the symmetrized matrix, which is important, in fact, in this folding construction too, that like, given a non-symmetric Cartan matrix, if you want to, you symmetrize. Having given you the full statements for the non-simply laced guys, let's now simplify our lives and have G simply laced so that these subtleties will not appear. So, exponential, sum over all modes of just the modes here over K, let's say Q, Y to the K. Okay? So these, if you're not using Q numbers, these operators are very famous. But here, in fact, there's two sets of such operators very naturally. Here I chose a preferred Q. On the denominator, I could have done the exact same thing and have 1 over T instead. But here, I will not consider these operators for what I'm going to talk about, but there's two sets of operators, these and these. One is defined with respect to the parameter Q on the denominator, one is defined with respect to the parameter T. We'll explain what this means. Okay, and now define the 8th screening charge, again, A runs from 1 to rank G, as just the integral of a screening current. Well, the integration contour has to be specified, but that's the that's what you would do in Dotsenko-Fateyev, free field, free boson, Coulomb gas, all these names mean the same thing, formalism. Okay? Now, why do I do this? Well, this is in some sense very close to the BRST Drinfeld-Sokolov reduction construction. I want to construct the generators of this algebra, to define for you the algebra, as whatever commutes with these guys. So the commutant of the QAs are the generators of this algebra. So QT is defined as the subalgebra of, well, I should be careful how, I'll just write associative algebra of all operators which in the commutant of QAs. So you have to consider both sets of screening charges when you set the statement. You construct by brute force all operators which commute with this and with this, the set of screening without the hat. In fact, they're redundant. That's why I'm only considering one set. For the purpose of identifying the algebra, you only need one set of screenings. And so that's what the W-algebra is defined as, okay? Just the set of all operators which commute with the QAs. So now the question that's going to be important for us, and in the context of Langlands, is what are the vertex operators? Okay. So the simplest vertex operator was introduced by Frenkel-Reshetikhin in their original paper. And it's an operator they write as this. So first option, we'll explain what each operator does and why it's relevant. So this is an operator that looks like exponential of very simple. Yes?
You say all operators within which feature set?
Ah, yes, so I should be careful. So here, I should consider the Fock space, the zero modes that I haven't written down. So zero modes generate some Fock space. So if I write down alpha A of 0 acting on like some higher state mu, so maybe I'll write it like this, V mu 0 equals some simple root mu 0. So this is the highest weight of a Fock space representation of your Heisenberg algebra. Okay? So the action of the zeroth mode on this vector is this eigenvalue times the vector. So this is an eigenvector, and this is the eigenvalue. And so you consider this Fock space, and you're just out of this Fock space representation of your Heisenberg algebra, you're looking at the subalgebra of all operators which commute with the Qs. Like this space has like many operators a priori. Like, I mean, so here's an example. Here's an example of an operator. Didn't have to be this one, but I mean, that's the point. I'm going to give you other operators that you can write down, but I'm saying that whatever commutes with this setup of operator, where the alpha satisfy these relations, and the zeroth mode are defined here, this subalgebra, that's what we call a deformed algebra. So in physics, it's not a surprising construction because this commutant is an intersection of kernels. They're literally, this is a BRST construction, which is the Drinfeld-Sokolov reduction in this case for WB. The same exact construction goes through where all these Q analog numbers are just numbers. And this is very well understood to be the construction of a W beta algebra. So alpha A 0, so here I have alpha A k, where k will now be an arbitrary integer. When k is a non-zero integer, these commutation relations are satisfied. The zero mode commutes with all the non-zero modes, and the zero mode is defined as just producing the highest weight of your Fock space. Yes, let me write this. This is true, I didn't define this. This is the 8th positive simple root of G. So the simplest step operator you can write down is this one, as absolutely. So what originally, when it was defined, it was written in terms of modes that are not new. They're just a rewriting of the alphas in a different basis. So the alphas are related to the to these new modes just by a redefinition. Alpha A of k is the sum m goes to 1 to r of w k b c a b q t. So you can think of these modes kind of being root type modes, generators. In Lie theory, in classical Lie theory, these would be fundamental weights and these would be simple roots. And this is how you'd write a simple root in the fundamental weight basis. But this is kind of just a Heisenberg algebra analog of this. So you just rewrite, like this relation uniquely specifies what these W's are. Just a rewriting a different basis to make this operator look pretty. If I write it in terms of the alphas, which I can, it would look very ugly. Yes, absolutely. K over 2. Yeah. Yes. So this is the simplest operator. Why? So what is the relevance of this operator in our story? Right. So I have a Riemann surface, told you with punctures. So there's a deep relation already pointed out by Frenkel-Reshetikhin in the original paper between the generators of the W-algebra and characters of fundamental representation of quantum affine algebras. So this was very surprising to them. This came as a surprise, that if you write the generators, we define them here, they're the commutant of the Q's. So if you write the generators, there's R of them, the rank of the algebra, R generators, that these generators are all written as a Laurent polynomial in those operators. So that's a surprise. Didn't have to be the case. In fact, it's remarkable that it's the case that the generators, which are, you know, like a nasty expansion, actually can be repackaged into a sum finite polynomial, Laurent polynomial, in these operators. So Y's and Y's inverse. They all start. It is not exactly the well group. It's only true in the Nekrasov-Chetashvili limit. Because now there's derivatives as well that show up. But something that Frenkel-Reshetikhin noticed back then, which they had noticed as a curiosity, and then Nekrasov, so this is Frenkel-Reshetikhin 98. And indeed, like, so back then, so maybe I'll write Nekrasov Frenkel-Reshetikhin in 2014 or 15. Nekrasov reconstructed these generators. So here, originally, they were called QT characters in the original paper. Nekrasov calls them QQ characters. To my knowledge, he wasn't aware that they were constructed in 98. So that's why they have new names. So these are the exact currents here, but constructed through a gauge theory construction, where in gauge theory, you consider a 5-dimensional theory on S1 times CQ times CT. Maybe I should write this more as a cigar. Whatever. And you consider a point defect at the origin of CQ and CT. So here I really mean some equivariant rotation by Q of a complex plane. That's all I mean. And the defect would wrap the S1. So they look like Wilson loops. They're points on CQ times CT, and they wrap S1. So from the point of view of 5-dimensional gauge theory on a circle, 5D Yang-Mills on a circle, these guys are Wilson loops. Wilson loops. And so you can carry out a localization computation of what the VEV of these loops should look like in this background, and you'll find that the VEV looks like the exact Laurent polynomial sum of such operators. Okay? And so the surprise is that this is not just an arbitrary Laurent polynomial. It looks like it's well, the various terms that show up are all terms are weights of fundamental representations of U H bar G. I'll write Langlands dual. Even though in the original paper, this was not written that way, it was written as UQ, but also it was written as a deformation of UQ. So it was unclear what the quantum affine algebra should be. And G was the same G. But whether or not you decide to work with G or G Langlands dual is kind of a matter of convention. You just call co-roots in one, weights of the other. So that's not a fundamental distinction. But what they noticed back then is that the argument of every one of these operators did not depend on Q or T separately, but depend on the ratio Q over T. So you'll have an operator that looks like YA, Q over T to some power, Z, to also some different power, whatever. So all the terms will be insertions at Z of like a defect, or in this case, well, Z will be the mass of a fermion in this realization. But anyway, so all of Z is always shifted in this expression by a specific amount, which Nekrasov writes in his paper, is a curious fact, Q over T. No explanation. But Frenkel-Reshetikhin also noticed it. Everything seems to depend on Q over T, and in this specific ratio. So very surprising. So that's already, these very simple operators have a deep relation, it seems, to the representation theory of quantum affine algebras. So that's the observation one. Now the next operator you can construct in order of complexity. Now we're in the simply laced world, yeah. Everything here is G simply laced. There's statements for G non-simply laced. I will completely skip. So the next order of operators is VA of X, exponential, the same exact generators, but now divided by a Q number. So, okay, what's this? Or KT. Okay, so some denominator. So these were constructed also in '98 by Frenkel-Reshetikhin, and they're called fundamental in that paper, fundamental vertex operator. The motivation here came from physics. They were trying to understand a completely different problem, which was which came from a totally physics perspective called the RSOS integrable model. And this is a vapor crystal interface as you change temperature in physics, and you can model this vertex. The dynamical symmetry of this model is a quantum deformed WQT algebra. So back then they were constructing for G equals A1, the first, I think Lukyanov and Pugai constructed WQT of Virasoro for G equals A1 as a dynamical symmetry of an integrable system. They were studying a solution called the Baxter solution. Well, anyway, but so these, in Virasoro, you have these operators, which I'm using a notation from minimal models here. So these are like integers labeling certain null states in a Fermat module, but these are natural operators to consider in Virasoro. So these operators, these fundamental vertex operators, they're the generalization to all G of these operators you find in Virasoro. And so if you take the one I wrote down, you get this operator. And if you take the one where the denominator is a T number, and you get this operator. And so that's the generalization to all G instead of just Virasoro, all G instead of G equals A1 and q-deformed. So it's some q-deformation of these operators which enter this model, which are, just minimal model, the simplest guys you can write in the minimal model of Virasoro.
These Y's have an actual conformal limit?
No. These are the only ones that have a nice conformal limit, and precisely the conformal limit is these operators, or the G version for all G, or G simply laced, of these operators.
So in the physical world, there's something more fundamental than these Y's.
Yes. Yeah, exactly. So that's also something that we had found like 10 years ago, because the primary vertex operators were also written in terms of more fundamental operators, which we're also going to show, like are in fact constructed from this algebra entirely. So like there is something more fundamental than the T's operators, which are the Y's, and for primary vertex operators, the same exact thing happens. So let's get there. So these have a nice conformal limit indeed, and they become these nice operators. These are important. Yeah.
This Y is like ratio of this B. So it's a B.
Yes.
B inverse C.
Yes.
That's why they squeeze the sort of caps.
Yes. There's some nice thing here about D brane, anti-D brane annihilation to dp minus 2 brane, which applies to not only to this, but to the next set of operators. I do not understand exactly why this works, but indeed, yes. So these, if you collide two, you get back, or vice versa. No, that's right. No, absolutely. But there's a nice story there to understand in string theory too. So in the gauge theory picture, 5D Yang-Mills on S1, the same thing. I have my circle. So now, so this would be the operator I wrote down. If I take Qt, I would instead have a defect that wraps this plane. And so these operators were the operators. So this would sit here, and this would sit here. They wrap the circle, and they wrap one of the two CQs. So yes, in string theory, they'd be engineered by D1 branes. These would be engineered by D3 branes. In fact, there's a nice story here too. I mean, you see it in the equivariant volume of these operators. This has no denominator, so it's supported at a point on CQ times CT. This has a denominator Q, so its equivariant volume should be such that you're wrapping CQ. And vice versa here, you're wrapping CT, equivariant volume here, which would be represented by this factor. So that, yes. And so these were the AFO operators. AFO, Aganagic-Frenkel-Okounkov, they studied conformal blocks with these particular operator insertions. So the way it works in WQT of G simply laced, you consider a block, and by block I mean the following thing. So you have up product A goes 1 to rank G, QA and A, product G equals 1 to L, VA or VD, sorry, VD XD. And this acting on a V mu 0. So this is the highest weight of, the highest weight vector of a Fermat module of weight mu naught, and that's the mu naught that I might have erased from the zero mode of my Heisenberg generators. This is the lowest weight vector of Fermat module, and these guys are the screening charges, the screening operators which I erased. Q equals integral screenings. So they're integrals, these expressions. This is an integral representation of a block, which again, just describes like a tensor product of modules, well, a subspace of such a tensor product, described by the weight subspace is, maybe I should write it as, well, let me write it down. So these are operators, they are these operators. So if you study this, quantum Langlands correspondence, the insertion here was of these fundamental vertex operators of Frenkel-Reshetikhin. Okay, so these are the charges, the screenings. So at each point, here I'm going to put mu infinity, here I'm going to put mu 0. At each point, you insert V1 at x1, V2 at x2, and so on. So all of these guys, A, runs from 1 to rank of G. So, you know, they're labeled just by the fundamental representations of G. Okay, so A runs from 1 to rank G. Okay? Yeah, I should probably have a multi-index or something. Yeah. Some AD or DA maybe. I'm not sure I can do that on the spot, but yeah, so for each insertion point, I'm inserting some D1, D2, so DA maybe, something. So, and here the last one maybe. So this is at XL, X2, X1, anyway. So that's what they were computing. Blocks were these integrals, which you can explicitly evaluate. They have a beautiful geometric meaning, they have an enumerative geometry meaning, and so on. And they have a meaning as certain partition functions, computing indices, supersymmetric indices in 3 dimensions, where the 3 dimensions are these. It's a partition function on a cigar times a circle with a topological twist. And so these are very well understood physically and mathematically, these blocks.
Sorry, also, over there you plot 2 cigars, CQ and CT.
Yeah. So CT is not wrapped in this picture by nothing. If you wrap it, I put the color orange. I would use here a different operator, which is the Q number, the T number.
There's another set of
Yes.
operator?
Yes. Absolutely. So they do not consider this operator, but you absolutely can. And the story goes through there's a similar story for inserting not the V's as they did, but you can also insert these operators. And so now you have to compute an index again, but with a different set of, different defect. Anyway, so that's the story here. Now on the U H bar Langlands dual side, what you're computing is V mu infinity product phi I phi D XD. Probably I'm committing the same problem. So these are again highest weight Fermats, where the highest weight is the same as these by rescaling. Just rescale, I mean, instead of mu, I wrote nu, but think of them as like just related by rescaling. And now you have these operators, which are the vertex operators of, well, that you would insert here. And these you should think of them as intertwiners. Between Fermat modules tensor product a fundamental representation, which maybe I write rho D or D, but it's an evaluation representation. So this is why I'm writing it here, XD. So intertwiners, so basically these guys, they're labeled at a position. So from the point of view of representation theory, you better have an evaluation representation somewhere to tell you, well, you're inserting an operator at a point. That's exactly what an evaluation representation will do for you. And so these phi's, they arise as like some, so this is some analog, Q analog. The Q version, which is well defined, of an intertwiner from a Verma module to Verma times a fundamental representation. Of what? Of this quantum affine algebra, which I'm going to write in terms of just the finite guy. So these, in terms of finite modules, the quantum affine representation can be written as just in terms of these guys. So I'm just going to write it like this. So Verma to Verma fundamental. What this means in simple terms is that from the point of view of the Langlands dual algebra, here I'm inserting an operator that's labeled by fundamental representations, really, or some intertwiner, but like let me just keep track of this data. And so this is not the same V. Maybe I should choose the notation slightly differently and write it like this or something, right? So these are like the fundamental representations of the quantum affine algebra. So this is a representation Langlands dual 1, rho D, rho 2, rho L, Langlands. So whichever way you want to compute the block, you can compute it from the quantum affine perspective in terms of these intertwiners, and they've been constructed and they're well known, and there's integral formulas for them, which were generalized by Aganagic-Frenkel-Okounkov to very general equivarieties, but anyway, integral formulas are known, and integral formulas are known on this side. This is an integral of screening currents. You can either compute by residues or look at the integrands and compare contours, but at the end of the day, there is a correspondence, an isomorphism of conformal block between these two things. They're not equal. I mean, this is a scalar, this is a vector. It solves the QKZ equation, so it's a vector solution. So you have to pair it with a covector or insert certain k-theoretic stable envelopes in the construction of Maulik-Okounkov in this language here to turn these scalars into vectors to have a real match. But nevertheless, there is an identification of those conformal blocks. So that's where these operators were introduced. This, well, it's phi d xd is this intertwiner map. They're arbitrary Verma modules. Right, so the map just says, like, given a Verma module, like produce some other Verma module tensored with like a fundamental representation. And that's the only labeling here is the labeling of that fundamental representation. There's also some XD to some number.
You were saying it's like a cylinder and you put it like counters eventually.
Yes.
You just stack like you start around to the next around
Yes. Yes. So, I mean, here you should think of this block in this language as valued in a certain weight subspace of, you know, like, so V D1 times V D2 times and so on times V DL nu 0 minus nu infinity. So like this comes from like these right here, right? So literally that's what we mean by conformal block. So out of this tensor product, a conformal block is a map that takes as input a tensor product of modules and outputs like some identity, some trivial module. So here we're working in this weight subspace of weight this. That literally is what this means. Okay? Okay. So, right, so these are the operators. So now there's another class of operators. So in particular here, the relation to quantum affine algebra. So we started with the WQT algebra, and we found a relation to quantum affine algebra through this conformal block procedure. Right? So for the Y operators, which were not vertex operators proper, which I've erased, these guys, like these were on the nose, kind of have a nice relation to quantum affine algebra through this theory of characters. Here, we have to do more work. With this fundamental vertex operator, we had to consider blocks and show that there's an isomorphism of blocks to blocks of the quantum affine algebra. But this is a very nice story. Now, let's do the last order of complexity, and we'll explain how it works. How much time do I have? I can look at it and improvise. Okay. Okay, no problem. Thank you. So there's some very nice representation theory here that I'm going to go slowly over so that we can all do an example together and see exactly how this works. It's very nice. Okay. Okay, so what's the next type of operator? And now we've reached in this series, again, very naturally, I'm going to write it as a lambda of x exponential sum k different from 0 WA. So I'm going to put a minus here, but I should have put minuses everywhere. So I'm just going to remove the x to the k. And now I'm going to put two quantum numbers. So these, surprisingly, were not considered by Frenkel-Reshetikhin. The first time that they appear is in an appendix, I think, I've really looked, of Aganagic and myself. 15, sorry. But they're very natural from the perspective of studying defects in gauge theory, because now all we're saying is, well, consider a defect that wraps S1 times the cigar times the other cigar, right? So now we have something that wraps everything. If the Y operators were represented by D1 branes in string theory and D3 branes were the AFO operators in type 2B string theory, these operators are the next order of complexity. They're D5 branes in type 2B string theory. I'm not going to go in this language, but there's again a natural progression. And so here again, you see that the equivariant volume on which these defects are supported really is two cigars, like quantum number Q and quantum number T. So these should really be defects, heuristically at least. I'm not going to prove it, but that wrap this background in 5D gauge theory. Okay? So I don't know why these operators were never introduced or studied, but what we're going to find is that, well, they have a very nice realization in terms of this story up there, some modification, which Spencer knows well. I think he gave a talk about, at least for G equals A1, he very well understood, but also they're very close to the Y operators. They have a very direct relation to the quantum affine algebras. So in a sense, like they realize this, the relation of these operators in WQT to quantum affine algebras is more rich for this example. So not screening, but the V's. So in the same way that you can produce Y's from products of V's, I think from products of these you produce V's, but that's as far as it goes. This is again a D5 anti-D5 annihilation phenomenon to a D3 brane, which exactly like it works D3 anti-D3 to a D1. Here you have a D5 anti-D5 to...
Well, you can have like cancellation of cancellations, like bring 4 of them together,
Yes,
and then you will get Y.
yes, yes, but not S. I think she's talking about S. So S, yeah, no, I mean, these represent, I mean, the S are finite extent branes, right? I mean, these are all infinite. There's no risk, but you will produce the infinite D3s from putting 2 D5s. But you have to do something drastic because these are non-compact, whereas the S's are. You have to glue, yeah, yes. Yeah, exactly, via gluing, but it's a different operation, yeah. So let me just tell you roughly, we're going to construct, so these lambdas do not have a nice conformal limit, just like the Y operators. No nice t equal q to the beta, q goes to 1 limit. I call it the conformal limit because in physics, we really think of the conformal Toda algebra, as I told you. But a certain product of these operators does have a nice conformal limit. And this product will be entirely dictated by the representation theory of quantum affine Langlands dual algebra with H bar. So we're going to construct a specific product of these operators that is a good definition of an operator with a conformal limit, and we'll call these operators Q primary vertex operators. So a Q primary vertex operator will look like V, and it will be labeled by a bunch of weights at x, d. And let me write it over there, it'll be easier. So it's the exact same story now. I'm going to reconsider blocks if you want, but instead of putting these operators, so this setup mathematically that I just described is called unramified. By this, well, mathematically it should be called ramified at 0 and infinity because you have Fermat module insertions there, and unramified at L points. Okay? So here we're going to consider a setup which is similar but fully ramified. So this is where this title comes from of tame ramification, tamely ramified. Tame just means what kind of singularity behavior you're allowed to have when you insert a vertex operator at a point and you bring points together. Or so the tamely ramified is about the regularity of the operators that you insert, and the ramification means that you're dealing with Fermat modules here. So in the story of the quantum affine algebra, the story here is just to insert now Fermat modules. So here I'm going to consider an intertwiner that intertwines between Fermat modules. And so I have Fermat times Fermat. Okay, so that's a very natural thing to do. It was very unnatural in some sense to why focus on fundamental representations. Fermat modules are okay.
This is a Fermat module of finite algebra.
Yes.
Okay.
It's Fermat module I write of U H bar, not.
So it's just response to like non-integer, non-dominant weight, non-integer weight of a finite GL.
Yes. Yes. Yeah, exactly. Yeah. So this guy, so the module that this appears in a decomposition of an affine module. So if I'll write this later, you'll see how it appears. But yeah, I'm writing this indeed as the finite guy. And so here I need to introduce new operators, which are these operators we're going to talk about, labeled by a bunch of weights at xd. So the Fermat module side of the story for quantum affine algebra, it's very natural to consider these operators, and it's well known that these have integral representations, and you can just consider now inserting such Fermat modules. Yes? So, tell me again, sorry.
What's this subscript? The D and
Oh yeah. Yeah. This give me 15 minutes, and if it's not clear by then, this is going to be now the main meat of the next 15 minutes. How to define this operator, and I have not defined what this is yet. This is a bunch of weights in the quantum in finite dimensional representation, in fact fundamental representation of a quantum affine algebra. You're going to have to find like I'll explain exactly like what this is. I'm not there yet. I'm just giving you the final answer, and now we're going to construct it. Okay, so on this side here, you insert x1 vd. So you insert here these new operators. Maybe I'll write a tilde to distinguish them from the Reshetikhin-Frenkel operators, which are labeled by some weights, and these weights are going to be quantum affine representation weights. So that's the modification I want to talk about. And I want to construct these operators. They have no definition. And so, there's one thing you can say is like, well, if you want the quantum Langlands correspondence to be true, to remain true for Fermat modules, then there must be an operator here such that this duality goes through. So
you're saying
the bottom line is well defined. It's very well known. And the top line must mean something.
What is the definer from one Riemann to
What is that? Yes. So the first solutions of this kind were constructed by Matsuo and then Varshenko in the 90s. And so it's known what these should look like, yes. And so you always have Fermat modules here and here, like, I mean, you know, like the meat of the operator you insert in your block is intertwining with what. And the what is what makes the operator insertion. So here, you could, of course, consider much more general things than just fundamental representation or Fermat module representations. But for this talk, this now will be a Fermat module. And here I want to know what this is.
When you say that this second line is like a vector valued conformal block,
yes.
It's a vector value. Is it by vector value?
Well, so these solve QKZ equations, which is a set of equations. So each equation, you can think of it as a component of some vector. So they're a vector equation because they're multiple equations. So naturally, you can say, well, the set of equations solved by, it's like saying the R matrix is a matrix. But it's like a L by L space, and the solution are L by 1 vectors in an L by L space.
But here it's going to be infinite dimensional, right? Because your expectations then close to Riemann. Yeah, but secretly in 0 and infinity, but it's take ways up to right.
Yes, so.
Yeah, sure.
You're right, yes. So now we're going to explain what is the construction of this and why it's interesting. So let's see. I'm going to need to review some facts about representations of quantum affine algebras, just to be able to tell you the answer so you can appreciate it, and we're going to do an example.
So essentially what happens when you have these intertwiners, it's like, you have to think of it as like gluing pairs of pants together. And so each time you glue a pant along the garments, you sort of get the one with the x theta equal 3. So by the time you get to the end, you've got a tensor product of a bunch of other x guys. But because you've got the two guys on the outside, what you end up doing is extracting a particular weight subspace of the guy in the middle. And as long as all the garments are really high.
So the end goal, in about 20 minutes, I will give a definition of these operators. Okay, so to get there and for you to appreciate the definition, I need to review some standard facts about representation theory of this thing. So in the finite case, when G is not affine, the representation theory of quantum G is very similar, basically identical to the representation theory of G itself, assuming H bar is transcendental. Okay? In contrary, this thing is infinitely more complicated than the representation theory of G affine. So the quantization here is actually very complicated and was developed in a series of papers by Charrier and Presley in the 90s, based on the work of Drinfeld. And so we'll need a few of their results. So let V be let VA be a fundamental representation of U H bar G. Maybe I'll write it like this. So the finite guy. An affinization V hat of V is an irreducible representation of the quantum affine case, which, when viewed as a decomposition in terms of finite modules, looks like the following. VA hat equals VA with multiplicity 1 plus lower dimensional representations, smaller representations. So that's called an affinization of a fundamental representation. So it's a theorem that affinizations exist. Affinizations exist. In general, they're not unique, which is part of the nightmare, which is to study the representation theory of these guys. So affinizations exist, non-unique, but in the case where VA is a fundamental representation, or in general, if you have a finite dimensional, well, for fundamental representations, they're unique. So this is another theorem of Charrier and Presley.
So what do you mean by this? Lower dimensional?
Lower dimensional, smaller representations, yes. Smaller irreps. So in general, these fundamental representations in these quantum affine algebras, they can be the same size as in the finite case, but they're generally bigger. In fact, in very nice way, like very interesting ways, but they're generically bigger. That's what happens. So affinizations exist and are unique for fundamental representations. And that's all we'll need to care about, because in this problem, all the defects will arise from fundamental representations. In fact, because we're dealing with fundamental representation, it's a bit misleading to call these quantum affine algebra representations. We should rather maybe say the loop algebra of G. The loop algebra of G, it's the quantum affine algebra mod anything that's in the, so this algebra has a central extension, and so anything that's, well, if you let the central element act trivially on your space, on everything, then this quotient is called the loop algebra. And so for finite dimensional representations, you're only looking at the loop algebra. In particular, the level of all these representations is 0. Level of all fond representation, or finite dimensionals in general, is 0. Okay? So, yeah, so what I mean by loop algebra, another way to look at it, right? So if it was just usual Lie theory, classical Lie algebra theory, the loop of G is G tensor the Laurent series in T inverse. Right? Laurent series in T. And then what I mean is like there's a short exact sequence, right, where you have the central extension G hat, L of G. And so literally this is the quantum, totally the quantum version of what you do in classical Lie theory, where you construct the affine representation by taking the, you know, like the direct sum on L, and it's a split exact sequence. I'm sorry. So here, yes, so the loop algebra in this case is actually all that will matter, because all the representations we'll look at are fundamental, or infinite dimensional in particular. So why am I telling you this? Because now there's a nice construction of the generators of the algebra starting from the loop algebra, right? So in the finite case, you have things like raising operators, lowering operators, and then the Cartan generators. And so here I'm saying that you construct the generators of your quantum affine algebra by tensoring with powers. So maybe this I'll call XAI plus. This is Drinfeld's second realization. It's called Drinfeld's second realization of quantum algebras. So this, if I have a lowering operator in the finite case, tensoring it with Ti, I is a is in Z. Okay, good. So here, this I will write as X minus. And if you take the Cartan elements, you end up with something that, not exactly, but I mean, I'll just write it like that. Say I plus minus. There's two sets of guys. And then there's the central element, which I will just ignore because it acts trivially. So in the intuition here is that now you started with a finite number of generators. A goes from 1 to rank G. By tensoring with T to the I, now I have an infinite number of generators, right? So, like in particular, if you were going to talk about the Cartan subalgebra, you have I goes from over all integers. So now I have really like a set of infinite number of Cartan generators.
So what do you have plus minus sign?
Yes, my notation is, there's a standard notation of Drinfeld on how to define these objects. I was trying to, if you've seen it, just reuse plus minus, but you're right, it's a bit awkward. The what, sorry?
Is the sign of pi.
Yes. Yes, yes. So in fact, a lot of the information I will be telling you will be redundant for one set of variables. So let me just restrict to I positive, and then because the representations I'm looking at are finite dimensional, there is a Cartan decomposition or Jordan decomposition of each fundamental representation, or each. Well, for any finite dimensional representation, I will write it as a sum V lambda, where V lambda is the V such that there exists a P for all K positive, for all, I'll write K, because I wrote K before. Everything will be K. I'll restrict to this. For all K positive, psi A K minus D A K to some power P equal 0. So this is this is some eigenspace decomposition, if you want, generalized eigenspace, because P can be greater than 1, of the Cartan subalgebra. So eigenspace decomposition. And it exists because VA is finite dimensional. So you can always write, so these guys are complex numbers. And they're called the weights of whatever this. So think of these as the Cartan generators acting on some weight vector, and they'll produce these eigenvalues, which are called the weights. So P to some V. Yes. So we'll put, yes, absolutely. Yeah. So the V equals 0, where V is this V. Yes. So that's exactly, yeah. So that's literally, if you're doing linear algebra, what you'd call the generalized eigenspace decomposition or the Jordan decomposition of a space. And so the point is that K, in the finite case, or the usual Lie algebra case for finite Lie algebra that we're used to, K would just be 0. But because we're doing this affine business, I have an infinite number of Cartan generators, but they all admit this decomposition for some P. Okay? So in particular, highest weights, maybe I'll... lambda will be the DAK. Absolutely. This is where we're headed. And now there's a formidable theorem which we're going to use, which is, well, so this is telling you, right, that so if I say P is 1, right, for the highest weight, say, of a finite dimensional representation. So as an example, if you have a highest weight, then you have like psi AK, and I'll just keep K positive, or 0, acting on V, the highest weight vector, equals this eigenvalue, V. Right? And so this is exactly like, imagine K is 0, right? This is literally the Cartan subalgebra relations for a highest weight. But now this is also true, perhaps to some, in this generalized sense, with a greater than 1 P, this relation will also hold for all the weights in your finite dimensional representation. And so now you can describe this representation either by tracking all the weights, there's an infinite number of them, or, and this is the magic, let V be fundamental, maybe also, okay, it works for any finite dimensional representation, but we're only looking at the fundamental ones. So for VA, so let DAK be as above, as in here.
Sorry, how does that depend on, how does V lambda depend on lambda?
This thing, yeah, so it's, it's the D's. This is not a good notation, yes. I should write VD or something. So D is a label for all of these eigenvalues. It's telling you that for a vector in your representation, well, the action of the size of all these infinite number of Cartan guys on V produces an infinite number of eigenvalues. And they're written as these. And okay.
Just making sure for K less than 0.
Yes. For K less than 0, there's another relation with other weights. There's a similar relation for. Yeah, so the information is somewhat redundant. Once you know the positive part, it will be enough for what I'm going to describe. But you're right that in the full algebra, there would also be the negative mode. They'll be related by a flip of sign to what I'm going to say about the positive mode. So it's not a. So the fantastic fact that I want to impress on you is that so you have now an infinite number of weights in your a collection of an infinite number of complex numbers. And the insight of Frenkel-Reshetikhin and Drinfeld and Chari-Presley in succession is that you can reorganize the generating sum of all these arbitrary numbers a priori into a very simple ratio of polynomials. So there exists a polynomial R, well, R of Z, maybe I'll write A plus of Z, A minus of Z, with constant term equal to 1, such that A plus A0 equals 1 equals A minus 0, and A equals 1 rank G. The sum of D, A, K, ZK, K different from 0, sorry, K goes from 0 to infinity, equals H bar to the degree of A plus minus the degree A minus times a ratio which looks like A plus H bar minus 1/2 Z, A H bar 1/2 Z, A plus H bar plus 1/2 Z, A minus H bar minus 1/2 Z. So these are valued in CZ. So you have polynomials with constant term equal to 1. And the magical fact is that for any one of these weights in finite dimensional representations, if you, instead of keeping track of them individually, if you reorganize them as a generating series, they are organized as the ratio of these polynomials, just simple polynomials. So these polynomials are called Drinfeld polynomials. Drinfeld polynomials.
So what is H bar?
H bar is the parameter that I have in my quantum affine algebra. So I had, I'm constructing representation theory of the finite, the fundamental, I'm looking at the fundamental representation of this algebra. On the left-hand side, there's no H bar. The H bar is going to be, this depends on H bar. But we're going to do an example right now so you see how it works. Okay? So let's try the simplest example. Example, evaluation representation. Evaluation representation of U H bar, I should write evaluation representation V1 hat of U H bar A1. So I didn't write for you the relations and constraints and that the generators have to obey on the algebra, but it's very easy to show given the presentation of this algebra. You can just start from Drinfeld's second realization of the algebra. You go through the relations and the generators have to obey. And in particular, you'll find that, so what do I mean by this representation? It's an evaluation representation. So it depends on a parameter. And here's how the action looks like. So because this is A1, I'm going to set A, I'm just going to remove the A label, which labels like the rank of G. The rank is 1 here. So I wrote it here as a, so this representation is the spin 1/2 representation. As vector spaces, it looks like C V0 plus C V1. This is the highest weight of the representation, and this is the lowest weight. There's only 2 guys. It's a 2-dimensional subspace. There's no what terms? No, exactly. No smaller. This works perfectly fine. In fact, for any fundamental representations of AN, there never is smaller guys. As soon as you go outside of AN, you have smaller representations, and there's a beautiful story there about how these things are related to defects that in tamely ramified Hitchin systems that were called rigid and so on, but we won't have to. No. In fact, I think by definition, because all of these you get by while action, so that it would imply that it's not going to happen. So psi 0, okay, so what happens if I act with the generator psi 0 on V0? Like the eigenvalue I get is h bar. So we were asking, where's the h bar? So the d for k equals 0 and a is 1. I mean, it's the A1 case. So I'm dropping the A label, as I said, right? So now I'm writing everything as dk for the A1 example. So for the 0th mode, the usual Cartan finite guy, psi 0 acting on the highest weight produces this. Okay? Now I have another, well, let's look at the infinite number of other modes that I have. Psi k acting on the highest weight state, what do I get? So this is a very short computation, but you can show that there's always this problem of 1 versus 1/2. Okay? So that's the highest weight. Let's just do the highest weight. Okay, so then I have an infinite number of eigenvalues for k, all k's, and the 0th mode. So, okay, we're done, right? We've characterized all the weights. Now the theorem of Drinfeld and then Chary-Presley. So Drinfeld formulated it for Yang-Yans, that's why I say Drinfeld. Chary-Presley did it for quantum affine algebras for the highest weights, which is what we're doing right now. And Frenkel-Reshetikhin extended this to all weights inside a finite dimensional representation, not just the highest weights. So here V0 is the highest weight, this is just Chary-Presley. Okay? So sum d k zk k 0 to infinity, well, something really nice happens where it's like h bar plus sum k 1 to infinity of h bar 1/2 minus h bar minus 1/2 ak zk. And then you recognize a geometric series, and so you get h bar to the 1/2. So I'll put this over 2. 1 minus h bar to the minus 1 a z over 1 minus a z. Okay, so this kind of, okay, I mean, yes, it's a geometric series, so what else? But the fantastic part is that it always takes this form. So then from the identification of this theorem, that means I have a polynomial a plus of z, which is 1 minus h bar to the minus 1/2 z, and an a minus polynomial, which is just 1. So it's a degree 1 polynomial with constant term 1, and the roots of this polynomial are called Drinfeld roots. Okay, so that's the highest weight. And so that was described by Chary and Presley. They didn't consider a minus polynomials. They don't appear for highest weights. You only get an a plus. But for any weight in a finite dimensional representation in general, you'll have a plus and a minus. So 2 sets of polynomials. And that's the theorem of Frenkel-Reshetikhin. It's just an extension to all weights. Yes, where's a? A, and I should probably put an a here. A. So a is the evaluation representation parameter, which, I mean, you're free to rescale, in fact, a to, so the presence of the h bar here is a little bit misleading, but anyway. So that's that. You can redo the exercise for V1 for the lowest weight, and you'll find a similar example. I mean, if I do it explicitly very fast, like if we now do psi 0 lowest weight, you get h bar to the minus 1/2 V1, and the other guys produce minus h bar minus minus 1/2. Okay. And then if you carry out this procedure and you reorganize dk, zk, k equals 0, infinity for the, so this is for v, I should write a label maybe, huh? Right? So this is like v1 and this is like v0. You get h bar to the minus 1/2, 1 minus a, h bar 1/2, z, or 1 minus a, z. And this was, yeah, actually just 1. So it's very similar to what we had previously. In this case, a plus is trivial, a minus is non-trivial. It's 1 minus a, h bar, z. Okay, so all these infinite weights can be repackaged into polynomials, and those polynomials are uniquely characterized by their roots and their degrees, because the constant term is fixed to be 1. So now let me give you the definition of the vertex operators of the W-algebra that go in the ramified setting. They're defined in terms of these Drinfeld polynomials. So that's kind of the surprise. So for this correspondence to work, if you want a necessary condition, is that these V's have a very special form, and the form they must have is the following. So definition. Q primary vertex operator of WQT G is labeled by J weights lambda. So the D's I wrote as lambda in the, because I don't, well, in UH. So these are weights of finite them inside the fundamental representations. In particular, they're only in the loop algebra. So where H bar is Q over T, and J parameters X D, which are valued on C star, the Riemann surface. Subject to the following constraints, with two constraints. They're not just any weights. Well, so the lambdas must appear. The lambdas must appear in the decomposition VA equals some lambda VA lambda for some A okay. So this is saying that the weights must be found inside fundamental representations, not more general ones. They all occur in some, they're found in some finite module that sits inside the decomposition, the Cartan decomposition of a fundamental representation. Okay, but they can be anywhere in that fundamental representation. Doesn't matter, as long as they appear in that decomposition. And the second constraint, this one is a bit more funny, but I'll explain what it means. For all lambda S in the set lambda, let A plus minus lambda S be be its Drinfeld polynomials. Comma B, it's because in the way I wrote it, yeah, so you see, so there was a problem I encountered here, which is in my notation. I think I needed an extra label for which weight I'm talking about. So I kind of fixed it like roughly here, but here I should write like each of these A polynomials. I should really write this as like D for the weight D. So each D has a set of two times rank G Drinfeld polynomials. So that's all I mean. So now my D's are lambdas. I'm sorry about the shift, but it's more easy that way. So you have, just write down the Drinfeld polynomials for each weight. Then the degrees of the polynomials must satisfy the degrees. So sum over all weights degree of A plus minus degree A minus must be equal to 0. And the operator then V lambda xd is equal to product S1 to the size of the set, which I call J, B1 rank G Langlands dual, product I goes from 1 to the degree of A plus lambda S B of lambda operator H bar to the minus A plus lambda S B I X.
Back then, we defined like the generic primary.
Yeah.
Right. And so this is a story about the non-generic.
No, this is the story of all of them. So the generic ones, there's this, right? So it turns out that this story about the representations coincides with the usual representation theory of G for the generic operators that you're talking about. But it's an accident that it's like we never, the language was just not the correct one. So, but so if you just use the language of representation, in particular, I mean, yeah, so there's many operators for which the correspondence doesn't have a counterpart. If you just use the generic ones, we could have gone away with it. So for instance, the operator that you studied for A1 is completely insensitive to this story. You will not, I mean, I'm going to write the operator and you're going to be like, oh wait, this is exactly the operator that maybe I would have considered for my Verma modules. But I'm saying like, it's kind of an accident, a happy accident that happens for certain weights, but in general it's just wrong. It's like saying that.
It's like for FL2, the only keys are
Yes.
E and G.
Yes. In fact, it's the ones that I wrote above, so you will find it. So there's this, and then inverse operators, J degree over all the minus polynomial, H bar minus A minus lambda S B J X XS, all right?
Sum over X is what? Sum over all the weights?
Yes, J equals the set. We used to have a relation which is let's have the sum of the weights equal 0. So this is fine sometimes, but this is the correct statement. So the degree of the, in particular, like there are certain things for which this is true, but for all the non-minuscule guys, this is true. But we just discarded them because we didn't know what to say. And so the statement is this, it's that, so what this means, very simply, is that if this solution, if this is imposed, then this operator has a good conformal limit. So at the level of the algebra, this is a necessary condition for just this to have a conformal limit. Okay, so why do I call them Q primary operators? Let's unpack a little bit, and then we'll probably be done soon. Because yes, so these guys, these labels, these are the roots, the Drinfeld roots. They're the roots of the Drinfeld polynomials. Okay, and now you have a product over like positive powers of this lambda operator, which I don't know if I did I erase lambda? It was I'll write it here. It's very simple. Lambda bx equals exponential sum omega b k x k kq kt. Okay, so these operators are the building blocks. They don't have a good limit. They should not be just inserted randomly into a WQT correlator. If you really want to describe these defects that wrap CQ times CT in 5D gauge theory, you need a specific product, and the product is defined in the following way. So basically, you just take a bunch of weights of your inside fundamental representation of the quantum affine algebra. So they're in the quantum loop algebra by default because it's a finite dimensional representation. And you should impose this constraint. And that ensures that the operator has a well-defined limit. So you can talk about this as being some kind of Q analog, right? So what we want of a Q deformation in particular is that when you take Q goes back to 0 or H bar goes to 1, you should recover an operator that makes sense. So if you take the conformal limit, what do you get out of this?
So these are still labeled by fundamental representation. Original say that the final structure. Write it down.
They're not labeled by the fundamental representation itself. They're labeled by weights inside an arbitrary number of finite dimensional. I mean, you can pick your weights in any fundamental representations you want, such that this constraint is satisfied. So they don't have to all be in the same fundamental representation. They can be in arbitrary fundamental representations. They're not labeled by the fundamental representation. No, that's the big thing. So your operators.
But somehow, are they labeled by fundamental representation of the quantum affine?
Yeah.
That's true.
No, your operators or the Frenkel-Reshetikhin fundamental vertex operators are labeled by
Those are very special.
So these are labeled by the fundamental representations.
And so what are these guys? Can you summarize it for us?
Yeah.
At least in my ears, it's very technical.
Yeah, absolutely. So the data here, I mean, when you write the operator here, right, is just a set of weights, and the weights themselves, I mean, so as long as they satisfy these two constraints, it's fine.
I'm not remembering how it works. Okay.
Yeah, so that's the.
So this constraint is to have a good conformal limit. That's what you care.
Yes. It has like some further implications why this limit is important. In particular, I mean, so there's a nice connection now well, so in the example we did, I mean, we've identified the polynomials. We could just write down what this product is, right? So for instance, in the case that you care about, which is like if you do like A1, so I just erase this, A minus Z equals 1 minus H bar 1/2 AZ. So for A1 example, you WQT of A1, well, I'm going to write down, I need to find a set that satisfies those two constraints. And so you can just write, well, lambda 1, it's hard to write what this weight looks like in a finite notation, but let me see if I have an easy notation.
So just making sure that I understand. So previously in that formula I have a D button on 1 to L with like the L counters. Here you have another J.
Yeah.
The J counters.
Yeah.
What does that mean?
Yeah, absolutely. So actually, there's this. It's funny. You should think of the puncture insertions as like XD is a center of mass, and so all of these lambda operators are shifted from XD by some small amount, by excess. Yeah, exactly. So I haven't defined how XD is related to excess, but precisely by what you say. So there's only one non-trivial operator you can write down for A1, because there's only one fundamental representation, and it's two-dimensional. And so, I mean, the two weights you can choose are V, and I'll write it in the Frenkel-Reshetikhin notation in terms of these Y operators. It's the weight Y and the weight Y inverse. It's just a sum of two spaces. We've identified the Drinfeld polynomials.
And then, I'm sorry, these H questions, they have to do with some R charges.
Yes, they are. Actually, just Q. But because for 13 equal 2, yeah, I mean, it's,
Right.
yes.
Did you have a single?
Yeah, so I was going to tell you now, like, this is actually literally a quiver description. The degree of the Drinfeld polynomials tell you the number of fundamental representation with Neumann boundary conditions, the degree of the,
Okay, go ahead.
so there's a story there, but yeah. So, but we have 10 minutes? No, less, 5 minutes. No. Right, so for this example, if you look at just, well, the lambda 1 is equals y. This is very schematic. Lambda 2 equals y inverse. You can check that the constraint on the degrees is satisfied. The degree of the A minus is 1. The degree of the A plus is 1. And of course, if I take those two weights, well, they belong in some fundamental representation, which is the fundamental representation in this case. And so I would construct Vx as lambda x1, lambda inverse. I'm normalizing, yeah, that's fine. So here I've just rescaled the roots by using the evaluation representation. It's just normalized. It's not important, but this is what the operator would look like. For A1, this is what you would insert. So of course, that's what we would say back then. What the hell is the point of H bar? You can just rescale it away by redefining X2. It's completely, this is not physical, right? So you could be just, okay, well, let me redefine X2. There's no H bar, but there's a lot of, yeah, exactly. But there's a lot of weights for which you cannot do that. So for instance, sometimes it can happen in SO8 or D4 that you have such operators, and then a redefinition by H bar does not do anything. And so the last thing I want to tell you, yeah, is a connection to, there's a dictionary one-to-one between this data and the representation theory, the representation of a quiver. Not of the Higgs variety, as is usually the case, of the representation of the quiver itself is dictated by this data. And so the quivers in question include a class of quiver known as Henshaw quiver varieties, but they're more general. This is a specific example, but so there's a nice story here to representation of a quiver, where the quivers look like this, say like, so this would be a UH bar D4. And so I'll write things in maybe a notation that's less happy for mathematicians, but because I only, the Higgs branch variety of my quivers is only a GIT quotient, another holomorphic symplectic quotient. I'm going to use what's called a 3D n equal 2 notation instead of the usual n equal 4. But so the quivers, they're labeled as follows, in fact. So N1, N2, N3, N4. So what's the data? What are these integers N1, N2, N3, N4? Well, yes, probably, certainly. Oh, yes, you can. What I would just so generically, I'm saying like this is an example of such a quiver. You could expect to have arrows between nodes. I mean, so what people call handsaw quivers are quivers which are of this form, things like that. I'm pointing out that, I mean, you know, there's not, I mean, in this story, there's also, this is also fine. So anyway, so each of these arrows is labeled by the number of arrows between a node and a weight is a degree of the Drinfeld polynomial in positive for some weight lambda s for node 1, right? Because so the correspondence is on node 1, on node A, the number of fundamental hypermultiplets is given by the degree of the Drinfeld polynomial in this data. It tells you what is the matter content of your, or the framing that you'll have for your quiver. So the framing is completely determined by the Drinfeld polynomials. The degree of the polynomial is the number of fundamental hypermultiplets. The degree of the yes, each weight is now characterized by two sets of R, 2 times R, rank of G, like Drinfeld polynomials. So if I give you a Drinfeld polynomial, like for my first weight, say I have like a polynomial, well, I always have 2 sets. So I always have fundamental paired with anti-fundamental multiplets.
Why 2R? I thought you had, oh yes, 2R.
Yeah. And so what is the R charge of these? The R charge in physics of these multiplets is the Q to the Drinfeld roots. So the Drinfeld root. Drinfeld root, Q to the A plus minus. And this. Then you have also this, this mass for the adjoint Carroll multiplet, which also, so that's labeled by T. And so it also has a charge, and the charge, the T charge, is also labeled by the Drinfeld root in the exact same way. So that's why you said H bar. For the 3D equal 4 story, H bar is the natural variable, but here, like, I really want to compute like something with respect to Q and not H bar. I mean, like, H bar is not natural. Like, the blocks are indices that look like 3 trace minus 1 to the F, Q, J plus R over 2 times the flavor symmetry content. So, I mean, Q has a distinguished role that, I mean, I can't just put. Now, what R is interesting. Like, there's multiple choices you can do. One's the A twist, the B twist. From the n equal 4 perspective, identifying R gives slightly different answers. So here, I think this is the A twist that you want for to reproduce the blocks as written there. Anyway, that's
Well, you know, maybe get here circle.
yeah. Yeah. Yes. So these ends, right? So from the W-algebra perspective, they're the number of screening charges, the Qs. And from the point of view of the of the quantum affine algebra, well, you know, we're looking at this weight subspace right here. Right, so this, if you rewrite this in terms of the weights, of the quantum affine weights that I wrote down, the missing, the difference, the piece is n and a times the roots. So that's the interpretation. So yeah, so in particular, not all quivers are Hensel quivers in this story. So these quivers are more, they all have 3D equal 2 supersymmetry, but they're not all like Hensel seesaw quivers like this. Like it can happen that you have multiplets to the same node, just not coupled by a superpotential term. There's no superpotential of n equal 4 that you would have in n equal 4 supersymmetry. Yeah.
I mean, is the triple phenomenon given they only depend on specific ways? That's not some statement that theory has an anomaly in reaction. So it doesn't know about all the others, so that's something else.
So I mean
what breaks if I don't do it?
If you don't impose the constraint, say, or
if I stay with the so are you saying that only for this one guarantees to you that you have an unknown plus one?
Yes. Yeah. So when you say on this side, I have Verma modules. As you know, like let's look at Verma module representations. In particular, like there's many weights that will appear like as you write down the highest weight of that Verma module. I mean, certain weights will be weights that don't belong in, they're not highest weight of some fundamental representation. I mean, we're looking at just Verma module weights. So like I can cook up a Verma module highest weight here that I would want, I mean, I want every Verma module I can cook up to have a correspondence on the W-algebra side. And so a lot of the things we would have constructed in the past don't have a correspondence. There's a story on this side which is clear. It's dictated by the representation theory of the quantum affine algebra, but on the other side, it's not. We wouldn't know what to write down. So all the, yeah.
What's the physics meaning of these simple groups? There must be some meaning. I mean, there must be some other story other than that we want one number one. Otherwise, maybe not that. Well, it isn't true. I don't know.
No, yeah.
Some reason why these things all together.
Yes. So here there's different perspective on this well. So already like in 2012 and 2013, like when Nekrasov and Chatashvili were studying what are the saddle point equations of the partition function, they were noticing that this partition function looked like characters of quantum affine algebras, where like the shifts were given by the Drinfeld roots. So
but what the critical equations look like when they were apart?
Yes, so
the statement is that if you choose, parameters correctly, then you'll get a Drinfeld, right? You have to explain what's the original source. There should be something that forbids you from doing things different. There should be some rigidity to the story on both sides, not just on one side, so that it works the other.
Right.
Cannot be any other way.
Yes. So what I'll say is that every one of these theories has there's a existence, but I don't know about the unicity. That's hard to check, especially for quivers as a field theory proof. That's not known. But every one of these, so of course, like this is also a statement you're familiar with, which is that the Higgs branch of any one of these quivers, the moduli space of vortices of some 5D n equal 1 gauge theory on a circle. So all of these theories arise from a theory that looks like, like so the Higgs branch, yeah, so So there's existence. So in that direction, this exists as the vortex, half BPS vortex solution of these guys. The construction, I don't know if it goes the other way. So like whether, if I cook up any theory here and start to look at its half BPS vortex moduli space, do I always end up with a theory that satisfies this description? Or is it that it's just all of these theories, there exists a 5D theory, but it doesn't have to be that all Higgsing of 5D theories reduce to a theory of that sort. So that's not known in the other direction. I would be very happy if the converse was also true, that any vortex moduli space like ends up being described like this.
You can prove that all the ones of this kind arise.
Oh yes. So they all have an origin here, and here like it's, there's, yes. So how do you prove it?
Yeah. How do you know that it's not here? For example.
Well, yeah, so by proof, yeah, because a priori AR and BR, yeah, so no, for a finite R you give me, then you can prove it. Yeah, so if there's no proof in these matters for like, that works in general abstractly, it has to be fixed on algebra, and because the classification of, this classification of weights is finite, go through all weights for that algebra, find the vortex moduli space for each one of these weights, and that's the classification for this algebra. You know, there is a...
But it sounds like what you're saying is like, in the ultrasounds, you guys were thinking about Higgs in like very specific 5D equilibrium. Like for AN, you would just do like complete like...
Yeah,